Okay, let's learn something else. So this is another application of integration. And it's similar to the last one. We're going to find, we're looking at a picture like this again. So I have a graph in the XY plane, and there's one of these spinny arrows indicating that there's an axis of revolution, and we're going to find the volume of this that this shape makes if we, spin it around the axis of revolution. But this is a different method. So here's what we're going to do this time. We have this region. We are going to split it into a bunch of subintervals, and we're going to treat each subinterval as if it's a rectangle. That's all usual stuff. Except, so this time I'm going to take this like vertical rectangle. I'm calling it vertical just because it's much thinner than it is tall. And spin it around this line, and if you can visualize what my fingers are doing, it's going to make like a cylinder shape, or more precisely, because this does have some width. Like, I'm trying to draw it pretty skinny, but it has some width. It's going to make a shape like this. This is what I call a cylindrical shell. It's basically like a cylinder with a slightly smaller cylinder cut out of it so that it's hollow. And yeah, by the way, there's no top and there's no bottom. So it's just like the wall of the cylinder. So here's what's going to happen. Each one of these rectangles, when I spin it around, it makes a cylindrical shell, and they all have different radius, and they all have different height and all that, but they all make cylindrical shells. I'm going to find the volumes of each shell and add them together, and that's going to be my approximation for this volume. And then through the magic of integration, we do the limit as the rectangles get skinnier and skinnier, and it turns into an integral. Okay, here we go. We need to know the volume of a cylindrical shell. So the volume of a cylinder in general is pi r squared h. But what I need to do is I need to take the volume of the big cylinder and subtract the volume of the whole, which is also a cylinder. So let's say that the big cylinder has a radius of r plus delta r, and the little cylinder just has a radius of r. And let's say that they both have the height h. So I'm going to do the volume of the big cylinder, so that's pi times its radius squared times its height. And then I'm going to subtract the little cylinder, which is pi times its radius squared times h. And that's the volume of the stuff that's left around the edges. Okay, so then we do some algebra. So I square this out. This is r squared plus 2r delta r plus delta r squared. So I square that out, and then I just cancel something, because this would have a pi r squared h, and this also has a pi r squared h. So basically this goes away and this goes away, and I'm left with this. And now I'm going to do something just a little bit funny. We should think of delta r as very small. In the end, I'm going to do the limit as the width of these rectangles goes to 0, and the width of these rectangles is what ends up being delta r. So we should think of delta r as being very small. So this is a small number, and this is also a small number, but I'm going to tell you that this one is much smaller. If I take a tiny number and I square it, I'm multiplying it by itself, it gets way smaller than the number itself. So delta r squared is much smaller than delta r. So I'm going to just go ahead and say that this is approximately, just ignore this. And then that's approximately the same thing. So that's all I wrote here. Okay, so if you believe me, our approximation for the volume is I'm going to add up a bunch of things that look like this. Going back to what we were doing, each one of these rectangles has its own cylindrical shell, and I'm going to use this for each one and add them all up. So there's a sum, that's what this is for. There's a 2 pi, just like this. And then, well, what's the radius of a shell? Well, if I take a particular rectangle and I want to spin it around like this, the radius is just the distance from like the outside part to the axis of revolution, which is like the middle of the cylinder. So it's just the distance from here to here, which is just x. So that's my x, that's my r. And what is the height of a cylinder? Well, the height is like this, so that's my f of x, so that's here. And then what's delta r? Well, r was x, so delta r is delta x. So we get this. And now we imagine taking the limit as the rectangles get skinnier and skinnier, and a sum like this turns into an integral like this, just like we did before. Yeah, so we get this formula, and of course we're going to use cylindrical shells in situations where we might be revolving it around a vertical line other than the y-axis. And we also might do this whole thing sideways, where instead of y equals f of x, we have like x equals g of y or something like that. And so I want to give you a slightly more general formula. So more generally, here's what I remember. There's always an integral, and then there's some blanks for us to fill. In the end, there's always going to be either a dx or a dy, and the one we just did, it was a dx, but if everything was sideways and I had x as a function of y, then I would do dy instead of dx. I'm going to use the word slices again, and slice maybe, it sort of means the same thing it did last time, but we're doing something different with it. A slice is like it's like a very thin rectangle, so I'm sort of like taking the shape and I'm karate chopping it with my hand and imagining like a very thin like slice of my region. So I take a slice and I spin it around. What goes here, whether it's dx or dy, is it's the variable that you're changing to get different slices. And I could take my slice farther to the left or farther to the right, and the variable that I'm changing to do that is x. So that's why it was a dx in this scenario, but that's how you tell in general whether it's a dx or dy. Also, one thing you can remember is when you're using cylindrical shells, your slices are always parallel to the axis of revolution. That's why you get a cylindrical shell, as you take a slice and you spin it like this and you get a cylinder. With the one we learned recently, volume by discs and washers, the slices are always perpendicular to your axis of revolution. So that's another way of thinking of it. Anyway, this gets filled in with a dx or dy. I just gave you a couple ways to figure that out. This gets filled in with the appropriate limits of integration, whether they're x values or y values, and that's determined by this again. R is the radius of a slice, which is like the distance between the slice you're taking and the axis of revolution. And h is the height of your slice. Okay, so let's do something with that. Let's find the volume of this shape. So it's getting revolved around the y-axis, and this is our function. So this is actually exactly like the first setup that I gave you. We don't really have to look at the more general formula that I gave you more recently. So, Okay. Yeah, okay, I don't need to fit this whole page on there. So we're using this formula. And this one came with a picture, so let's trust the picture. I'm going to integrate a to b, so x goes from 0 to 1. There's a 2 pi, there's an x. My f of x is 1 minus x squared, like that. So that's my setup. So let's do it. I can pull the 2 pi out. And again, you can always do that. All right, so that brings us here. Now, there are some functions that you should be able to look at and immediately know what the antiderivative is. I wouldn't necessarily say this is one of them. This is not on my mental list that I have memorized. So in this class, we're going to learn a lot of tricks for how to find antiderivatives that aren't immediately obvious. But we really haven't learned many at this point. There's one that we learned in Calc 1, which is substitution. So typically people use the letter U for substitution. They call it a U substitution for reasons that will become apparent later. I like to use the letter W, but let me say what W is. And once you get this idea, the standard advice for what to make U, or in my case W, is it's the inside of a composite function. So if you're looking at your function, there should be something, and it's like you're doing something to x and then you're doing something else to x. So I would describe that, what's going on here. So first I'm taking 1 minus x squared, and then I'm doing the square root of that. So that's a composite function. That's like f of g of x, where f of x is doing the square root and g of x is 1 minus x squared. We let w be the inside function. That's typically good advice. When we do that, there's always a dw. That just means I take this derivative, which is minus 2x, and then I put a dx on there. It's just like doing the derivative, but you put a dx on there. It's called a differential. Okay, so here I go. This is a 2 pi. Since I have limits of integration, I can go ahead and convert these into w, because currently these are x values. This is an integral with respect to x, so these are x values. I'm about to write this as a integral with respect to w, so I would like these to be the corresponding w values. So how do we do this? Well, what goes here? I'm going to take this x value and see what w is. So w would be 1 minus 0 squared. So what goes here is a 1. And then what goes here, well, that's going to be the w value corresponding to this x value. So that's 1 minus 1 squared. So that's 0. All right, so that's just a review of how that works. Let's convert the rest. Yeah, let's see here. Of course, this is just the square root of w. That was the whole point of making that w. But I have other stuff going on. I've got this x and I've got this dx. Let me tell you, and there are multiple ways of dealing with this. Here's maybe the lazy way. I'm not saying lazy like a bad thing. I'm just going to keep this x exactly what it is. And this is not great, because ultimately I don't want x's in what I'm about to write, but I'm just hoping for the best. Now I'm going to take this dx, and I can replace dx with what I get over here if I solve it for dx. So let me just... if I'm just dividing by negative 2x, I just get that. Now I can replace this dx with that. And then I look back and say, hey, laziness paid off, because this x that I was a little bit uncomfortable writing, but I wrote it anyway, it just canceled. So now I have an integral with only w's and no x's. All right, so let's proceed. 2 pi, actually, so I've got a negative 1/2 here. I can pull that out. And then what I have here is a square root of w. Since I am doing calculus, I'm going to prefer to write w to the 1/2. And then I think I took care of everything. All right. 2's cancel. So I have got a negative pi times, all right, here now I'm finally ready to do the antiderivative. I go w to the 3/2, because for an antiderivative I increase the power by 1, and then I'm supposed to divide by that new power, so I'm supposed to divide by 3/2, but let me multiply by 2/3, because that's the same as dividing by 3/2. All right. And then I go like this and this. So I've got my negative 2/3 pi in front, and then I'm going to have 0 to the 3/2 minus 1 to the 3/2. 0 to any power is 0, or any positive power, and 1 to any power is 1. So this here is a negative 1, so I get 2/3 pi. And, sorry, just a second. Yes. So that's our answer. And let me just point out that we just found the volume of half of a sphere. That's the three-dimensional shape if I take this quarter circle and I revolve it around this, I would get the top half of a sphere. And we just found its volume the hard way. At some point, you may have learned that the volume of a sphere is 4/3 pi r cubed. And our sphere would have a radius 1, so the volume of the whole sphere would be 4/3 pi times 1 cubed. But of course we were doing half a sphere, so we should get 2/3 pi. So that's, again, math works. The answer checks out with what we know it should be. Okay, great. So let's do another one. And let's say that this is set up but do not evaluate an integral for this. So this comes with a picture, but I don't think I really want to trust my eyes too much. This is the line y equals 2 minus x, so it's clear enough that this hits the x-axis when x equals 2, like when x equals 2, y equals 0. So I trust that this point is, that the x-coordinate here is 2. What I'm not so trusting of is the coordinates of this point. So let's solve an equation to get it. Minus x equals square root of x. I'm going to square both sides. Okay. If I square this, I'm going to get 4 minus 4x plus x squared. If I square this, I'm going to get x. Let me get everything over, and I'll rearrange it. X squared minus 5x plus 4 equals 0. Factor x minus 4, x minus 1. So x equals 4 or 1. Now 1 I can believe. 4 seems kind of weird, but we did something when we solved this that can introduce extraneous solutions. An extraneous solution is an answer that you get that doesn't actually satisfy the original equation. Here's the thing. We squared both sides. When you square both sides, basically when you square a negative number and a positive number, or like a -2 and a +2, you get the same answer. And so that can introduce things that, situations where two numbers were not equal, and yet when you square them, they are now equal, and that's what's causing these fake solutions. If we just check this against the original equation, we'll see that x equals 4 does not work. Like if I plug in x equals 4 here, I get -2. But if I do the square root of 4, that's +2. So x equals 4 is extraneous. If I try x equals 1, everything works out. 2 minus 1 is +1, square root of 1 is +1, so we're good. All right, so we showed the work and we found the x-coordinate at that point. Okay, so we want to set up an integral. So let me sneak this on the screen, because this is like the general picture. And this is an example where everything is basically sideways, right? Like the original one had the axis of revolution as the y-axis. Now we have the axis of revolution as the x-axis. So we're going to be more careful. We're going to use the general formula. Okay. Let me write an integral sign. That's a good start. There's going to be a 2 pi involved. I could write that on the outside. Maybe I should have, but it's too late. Okay, now we have to think. Maybe let me fill in this box. So is this a dx or is it a dy? Remember, I'm going to use the word slice again. My slices are always parallel to the axis of revolution. And whether this is a dx or dy is determined by like what variable am I changing to pick different slices. So my slices could be higher up or lower down, and so I'm going to write dy. Let me leave myself a generous amount of space and write a dy somewhere. All right, I need to fill in the limits of integration. And since I just wrote a dy, these are going to be y values. So y is going to go from, okay, 0 up to, well, whatever the y-coordinate of this is, which technically I didn't figure out, so let me figure that out real quick. I found the x-coordinate at this point. I just want the y-coordinate. And this is where these two curves intersect, so I could really plug x into this formula or this formula, either way. I get y equals 1. So that's how high y goes. Okay, making progress. What else do I need? I need r and I need h. R is the radius of my cylindrical shell, so I imagine taking a slice, and it could be higher or lower. It's at some value that we'll call y. And when I spin that around, the radius is the distance between the slice and the axis of revolution. So my radius, I'm just going to write the letter y. All right, what do we still need? We still need an h. H is the height of my slice. And of course, when we say height, you have to imagine that everything could be sideways. Actually, in this case, normally I'm used to looking at a cylinder where the circular part is at the top and the bottom. Like that's why we call it height. But if I take a slice and revolve it around this, like I have to turn the picture sideways in order for maybe the word height to really make sense. So the height is the distance from like wherever my slice hits this curve to wherever my slice hits this curve. And I want those answers in terms of y. So again, what are we doing here? Let's look at it. Look at it right side up. I want the distance from where my slice hits this curve to this curve. And so what I'm going to do is I'm going to subtract two x coordinates, this x coordinate minus this x coordinate. I'm doing right minus left. And that means that I want to find the x coordinates. And these are given to me, solve for y. But that's no big deal. I can just solve it for x instead. So I'm going to fill in this set of parentheses with my h. The x value on the right, this is given by this curve. And if I solve this for x, here, let me show some work down here. If I solve this for x, I get x equals 2 minus y. So that's this x coordinate. And then I'm going to subtract this x coordinate. So that's on this curve, y equals square root of x. And I solve that for y. I get x equals y squared. All right. And now is a good time to remember that this was set up but did not evaluate, so we're done. Okay. Actually, I'll leave it at that for this one.